taking out one very specific part of the chapter, that is determinants, because it's going to help us do other things with vectors in a bit. So for right now, just know that a determinant is sort of like an absolute value of an array of numbers. But unlike absolute value, it's not always going to be net positive. You can get a negative determinant. But it is a way of turning an array of numbers into a single number. Okay? So we get AD minus BC. Ever see that with a 2 by 2? Yeah. It's just the difference in the products of the diagonals. So let's do this determinant. What are you going to multiply?
1 minus 3.
Yeah, 3 times 7 minus 4 times 2. 21 minus 8, 13. Notice you can do this on your calculator. And I brought along my calculators as well. You're going to find this very handy for the next test to have an 89 to do these. Okay. Now, you can actually go to the matrix menu, but it's a lot easier just to do it on the home screen. And these brackets are located right here, right there. See that? You got to use the squared off brackets to designate a matrix.
You have to type in the ED.
Yeah. You can look it up in catalog, but by the time you get to it, you probably type in ED. The determinant of, so you're using parentheses around the whole thing. But to enter a matrix, you have to give one set of brackets just for the whole matrix, and then another set of brackets for each row. Okay? Yes?
So this would be 3, 4 on the top and 2, 7 on the bottom?
Yes. 3, 4. You can put spaces in if you want, but I find it easier to do the comma than the space, because the space requires alpha press. And you don't put commas between the rows, because you've got the brackets to do that. You might think this is a strange way to do it, but actually the calculator accepts vectors with brackets, and then looks at matrices as a stacking of vectors of the same length. So if you were to just do and you can actually do a dot product of 2 vectors by using brackets as well. Okay? All right. Let's practice more of this stuff by hand. I want to make sure you're aware of how you can do it on your calculator. But you have to know how to do a 3 by 3 by hand for determining if we're going to understand the cross product. Okay. Now, to do bigger, before we get to the bigger determinants though, let's see what happens back here if we look at, let me just insert something here. What if I switch the rows? Does it matter? Now you have 8 minus 21, and you have negative 13. So which matrix, which row is on top does make a difference. Same thing if you switch columns. Yeah, for 2 by 2. All right. We mainly want to just focus on determinants of 2 by 2s and 3 by 3s. Yeah, you can do 4 by 4s as well. But the idea is it's a recursive process now to do determinants of bigger matrices. By turning a 3 by 3 into a bunch of 2 by 2s. By turning a 4 by 4 into a bunch of 3 by 3s. And this is what I mean by the minor of an element. It's what remains when you take out the row and the column going through that element. So, the minor of A in this matrix, let me get out my special minoring pen here. You look at A, and we take out the row and the column going through A. Okay? That leaves you with a 3 by 3. So that's RFELVMTND. That is the minor of A in this matrix. Because this is how you're going to do determinants of higher order matrices. The 2 by 2 formula is real easy, right? Yeah. Difference in the diagonals. Now you got to make sure you do it the right way. This way first, minus this way. Okay. So now to do 3 by 3 and 4 by 4, we're going to expand it by minors of a certain row or column. I just wanted you to have this idea of what a minor is. It's very easy to visualize. You take out the row and column going through that element. Okay. see? So you're going to have to keep on doing it recursively. So to do a 5 by 5 matrix, you'd set up the minors, all the possible minors of a row of column. You're going to see that in a second. Now, there's another thing you have to do with minors, and that's this: you multiply the elements by these changes in sign if the elements are in these positions here. What kind of arrangement does this remind you of? Chess, right? Checkers, chess, tartan plaid, okay. All of these have this kind of cross-hatching, where this, I mean, if you want a formal definition, you can take -1 to the row plus column number. So like this is in row 3, column 2. That's 5. -1 to the 5th would be -1. Easy enough. Now, let's see how this works. Evaluating this matrix by changing it into 3 2 by 2 matrices. Okay? We're not going to do every possible minor, because you might think, oh, there's 9 elements, and we can do the minor of each one of those comes to 9. No, you only have to pick 1 row or 1 column. So let's expand by minors of the top row. By minors of the top row. So you start by writing down 5, 2, and 8. 5, 2, and 8. That's the whole top row. And then you take the minor of each one of these. Since 2 is in a negative position, we've got to tack a negative there. That's how you incorporate the whole idea of a difference in primes, right?
So that's -2.
Yeah. That's sort of what happens when you do the determinant of A, B, C, D. The top row is A, B. What's the minor of A? D. Because when you take the row in column 3A, you just get D. And the minor of B, C. Now, we don't just add those two, do we? We said the determinant is the difference. So that's because B is in a negative position. So it shows up here too, this negative position. And almost basic formula. But see, I didn't start that way because it just, you might think, well, why are you doing it in such a strange way? It's easy enough to memorize the formula for a 2 by 2, AD minus BC. Now, the formula for 3 by 3, though, I'll talk about it, but it's not so easy to memorize. Okay? This process is easier to memorize because you can keep on extending it to bigger and bigger matrices. Okay, what's the minor of 5 then? 4, 1, -1, 6, right? Everybody see that? What we're doing is taking out the row and the column through 5. Leave behind 4, -1, 6. And then -2 times, notice 3, 1, 7, 6. And then 8 times
3, 4, 7, 8.
There you go. Now you can do these little 2 by 2s by the difference in the product of the value. So 24 minus a -1. Careful with your negatives there. That's usually where the arithmetic gets messed up. Plus -2 times 18 minus 7. Plus 8 times a -3 minus 28. Whew. 5 times 25. Plus -2 times 11. Plus 8 times -31. So you get 125 and -22 and -248. Oh, I hope we didn't mess. I'm getting 125 plus a -270 or a -145. -145. Where's my little answer? Yeah, you drive the calculator. I just usually have a little answer hanging out here somewhere. No, I didn't. Wait, isn't that the same one now?
Hey, wait a minute.
What the? Oh, we're going to do it a different way this time.
Oh.
Yeah. Let's expand by minors of the second column.
Whoa.
You can pick any row or column. Okay? 2 plus 4 times the minor of 4 plus negative 1 times the minor of negative 1.
But 4
Now,
is negative.
any adjustments?
4 is negative.
No, sir. 2 and negative 1. So this is negative, and this we change back to being positive. Okay? See that? All because we're taking the second column now. And so the minor of 2, 3, 1, 7, 6. The minor of 4, 5, 8, 7, 6. The minor of, now careful, which one are we talking about here? It's this one, right?
Yeah.
So what's left? 5, 8, 3, 1. So we get negative 2 times 18 minus 7 plus 4 times 30 minus 56 plus 5 minus 24. Oh, cross your fingers, people. Negative 2 times 11. 4 times negative 26. Is that negative 19? Yeah. Negative 22. And negative 104, right? And negative 19 looks like negative 145 to me. Yeah. Check. Did anybody have a chance to check it on the calculator?
I'm on, and she did it right.
Now, do you think it takes you just shorter doing the calculator by hand?
Probably, but
It kind of depends.
that's how big it is.
And what kind of numbers you have in here? And sometimes there's an advantage if you see some zeros. If you see some zeros, you maybe want to pick on that and use that in your row and column you choose so that you zero one of the matrices.
I remember this from freshman year.
Okay. Now, with 289, negative 145. So we're all set to go, okay? Yes.
If two matrices have equal determinants, does that mean that they're equal matrices?
No. It's kind of like if two numbers have the same absolute value. Or they're the same. Or if two vectors have the same magnitude. Because what you're doing is you're taking a complicated idea and trying to come up and associate with one number with it, okay? So there's not going to be like a one-to-one correspondence there.
Could you ever
Okay.
get this?
Could you ever which?
Could you ever get the determinant and then have us find a number in the matrix?
No, no. It's not, the determinant function is a function, right?
Yeah.
The inverse of a function isn't always necessarily a function because you have so many things mapped onto the same range, which is okay for a function, but not okay if you try to do inverses. Okay, here's the alternative way to do 3 by 3. What are the minors here? If I expand by minors at the top row, and notice I already put the negative there with the b. This is if you'd like to memorize the formula for this. What's the minor of A? EFHI. The minor B?
DFGA.
DFGI. Right, minor C? DEGH. So we have A times EI minus FH plus negative B times DI minus FG plus C times DH minus, is that E? What happened here? That's E. DH minus EG. So AEI, and sometimes Y, okay, minus AFH minus BDI plus BFG. Have you all read that book? CDH minus CEG. So AEI plus BFG plus CDH minus AFH plus BDI plus CEG. And if you look at these, it's the diagonals, right? But you might say, oh no, there's only 2 diagonals in here. Well, actually, there's more when you swing that over. So rather than memorize this formula like you did the AE minus BC, memorize the diagonals that these represent. So what you can do, let's extend this, is you make your A, B, C, D, E, F, G, H, I, and then repeat these columns, A, D, G, B, E, H, and then look at the diagonals. Our first set of diagonals, there's your AEI, big friendly giant, BFG, CDH, okay, so those match with these. So some people actually prefer this method for doing 3x3s instead of going by minors. I don't push it so much because it doesn't extend to the 4x4. I actually said not come up with a diagonals trick on the 4x4. It starts getting too complicated. And then you've got the other diagonals coming back, and here's your CEG. CEG. There's your AFH. And there's your BDI. Right? So that's one way you can do a 3x3 determinant. Of course, how do you do a 4x4 though? Because we're going to end with. You want to do the first column, why?
There's more zeros.
2 zeros in the first column. So if you pick that, you make things a lot easier. So now it becomes, right. In fact, we can do it like this. We can say 2 times the minor of 2, which is 5, 1, negative 2, 1, 0, negative 3, negative 6, 4, 2. And then 0, doesn't matter what that minor is because it's going to be multiplied by 0. And then negative 2 times the minor of negative 2, which would be negative 4, 7, 3, 5, 1, negative 2, negative 6, 4, 2, and then 0 times all that. So now it's a matter of expanding that out. Now, you want to try the diagonals trick? Let's try the diagonals trick. Diagonals trick. And some students like this too because they can maybe do a lot of multiplications in their head if they got small numbers. So you've got 2 times the frontways diagonals. 0, 1 times negative 3 times negative 6 is 18. Negative 2 times 1 times 4 is negative 8. And now this is 2 times all this. Minus the backwards diagonals are what? 0, right? Yeah. 5, negative 3, and 4 is negative 60. And then 1, 1, and 2, that's just 2. So that's not so bad at all. That's 2 times 18, and we said negative 6, right? Did we? Oh, let's go this way. Hold it. 18, it was a negative 8, yeah. So that's 18, negative 8, that's 10. Minus a minus 58, so plus 58. So we get twice 68, or 136. That's not the whole thing yet. We have to do this one too. Negative 2 times the frontward diagonals, negative 8, and negative 14, and oh, ouch. How about 84? And, oh my gosh, 60? Minus all the backward diagonals, negative 18. 16, 32. And finally, 70, right? Are you keeping up, gang? It's tricky. Is somebody racing me on the calculator? Go. See if you beat me this time out, okay? Because I'm almost there. 144 minus 8. 136, right?
Go.
Minus 92 minus 18. Ooh, no, that's 102 minus 18. 94, right? No. Yes. No, 84. 84, right? 18 off of 32 is 14. 84, right? So you get negative 2 times 52. So that part's negative 104. Pressure, Emma. I'm getting 32.
And I'm getting...
Okay, another race. Challenge you.
Race. And I don't know the answer, so we don't know.
Well, guess what?
I gotta trust you.
No,
Come over here.
32.
It's 32. I think it says in here. What section is it? 7? 7? 32. Okay. Bingo. Okay. Yes, questions?
So on the test provided, is it doing it on our calculator?
Yes.
Oh,
Any determinants I put in the calculator, I'm not going to just have you do a 2x2 determinant. We're mainly interested in the applications of this tool, and some of them can't be done in the calculator because it's a cross product. And I want you to show the cross product. The cross product involves using a 3x3 determinant, but having the top row be the identity vectors. We'll get to that. Actually, in 2 days. Yes?
So, for the 4x4, if you didn't want to do the 3x3 formula that
Yes.
you found out, could you just like take out another minor? And
Yeah, which row or column would you use here?
I would say the middle.
Yeah, so the middle row or the middle column would be handy because that's 0 in there.
Yeah.
Not so lucky here,
Right.
because it's
But
going
you
to be
could just
grueling
like take
down
it out,
in 2.
and then like if you were to take out the first one, you just multiply 2 by each one of those, then, right?
Right. So this -2, remember, is going to be multiplied by whatever you come up with for this determinant.
Alright. Thank you.
So you can take on any size if you have enough time. We're mainly concerned with 3x3s, because those are going to be this 2 and 2x2s, because those are going to help us with our vector analysis in 2 sections. And now this actually yields a number, a scalar.
What do the numbers in the matrix stand for?
Well, they can stand for an array of vectors. They can stand for the matrix. We're going to see tomorrow one of the applications that you use them to solve a system of equations by looking at the coefficients, Kramer's rule. Yeah.
First column, like, for example, is the first column like
Right. The first column might be the coefficients on x, coefficients on y, coefficients on z, coefficients on w. And then with Kramer's rule, there's a way you incorporate the constant column into this to come up with a very methodical way of coming up with a solution for a system of linear equations. Okay? Today, finally, you got 15 minutes of some group time and getting some stuff done. And here's oh joy. We got some 12-6 stuff here. Thank you, Michelle.
I put both. I put also 7 stuff on the board.
This time, is it okay if you do like, if you have
Hang on.
problems with 17 and 19, just to do them continuously on the same page?
No. That is a huge
Stop.